Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we move on with David Sontag, who did his PhD at MIT with Tommy Jacola. He's currently an assistant professor at NYU's Quran Institute and Center for Data Science. So David has made many fundamental contributions in the field of approximate inference and graphical models. He's currently interested in applications of machine learning to healthcare. And David received much recognition for his work already, such as Best Thesis Award, Best Paper Awards at EMNL, UAI, and NIPS, and an NSF Career Award. So let's welcome David.
All right, so this is joint work with Yoon Kim and Yassine Jernait, and my colleague Sasha Rush from Harvard. So ostensibly, this is going to be a talk about language modeling, but really behind the scenes, I want you to be thinking about representation learning, and I hope to inspire you to think about new ways to try to do representation learning. So language modeling is looking at, really, if you have a sentence of length 10, how can we try to talk about a distribution of such sentences? And language modeling is very important for many downstream tasks, such as speech recognition, machine translation, and text generation. So any distribution could be written using the chain rule as this factorized form shown up there. And the simplest approach to language modeling might be, for example, an n-gram language model, which says that we're going to look at the conditional of the likelihood of a single word given all of the previous words and approximate that as a simple distribution condition on the last n words. Now, as n gets larger and larger, the ability to estimate such distributions gets worse and worse, and one needs to use smoothing techniques for n-gram language models to actually be effective in practice. Now, our work is going to be in the world of neural language models, which takes a slightly different tack at this problem. Rather than representing words as a one-hot representation, we represent words using a word embedding. And then one attempts to learn a neural network. In particular, one takes a composition function g, a vector-valued composition function g, and attempts to learn a softmax distribution where to predict the probability of a word j is given to as the exponential of a dot product of a output word embedding, pj, dot producted with this composition function applied to all of the previous words, to the word embeddings of all the previous words. Now, there are many ways to try to implement such an approach. One of the simplest would be a feed-forward neural language model, which takes the past few words, comes up with the word embeddings for each of them, then it composes them some way, such as doing a projection into some hidden space, and finally it takes a softmax of that in order to do the prediction of what the next word is going to be. A slightly more elaborate approach is based on recurrent neural networks, where that hidden state h now is a function of all of the previous words rather than just the past few words. So that's done by having some nonlinear function f, which takes as input the new word xt and this hidden state from the previous time step ht minus 1, and then produces a new hidden state for the current time step ht, which is then used together with a softmax to predict the current word. So here's the picture of the current neural network setup. We've got all of the previous words so far. We get the word embeddings. Those word embeddings are then used together with the hidden state from the previous time step to compute the hidden state of the current time step. And finally, that hidden state is then used to predict the current word. So essential to the success of neural language models has been the use of word embeddings. And word embeddings has been shown time and time again to find a number of interesting linguistic structures. In particular, similar words tend to be close together in the learned vector space. Now, the natural language processing community has become really excited about neural language models because they simply work really well. So if you were to take, for example, that count-based n-gram model and look at a data set derived from the Penn tree bank, a measure of held-out likelihood called perplexity, where you want a lower number is a better number, would be something like 140 for those older approaches, whereas the most recent neural language model-based approaches can get perplexities which are dramatically smaller. And this has led to a lot of interest in the NLP community on language modeling. Now, all of these previous approaches use well, not all of them, I'll talk about some exceptions later, but the vast majority of them use word information at a word unit level. And one of the key challenges with such a thing is that if you were to look, for example, at the log frequency of how often every word appears in the corpora, there are a number of words which are very rare and which might be very difficult to estimate the corresponding word embeddings from the data, but they share a number of similarities with previous words that might be much more frequent. For example, here you see that the suffix ing occurs frequently throughout the corpora. If you look at prefixes as well, and many of these neurolanguage model approaches are going to be ignoring the fact that there are these similarities between words. Now, because of that, it makes it very difficult to learn neurolanguage models with rare words. And in this work, what we're looking at is how can one try to leverage sub-word information for language modeling. And from my perspective, as the introduction mentioned, I'm very interested in healthcare. And in healthcare, we have text which looks a lot worse than even Twitter posts. It has a lot of words which have misspellings in them, and those misspellings might occur only once or a couple of times in your corpora. So such an issue is really important to try to solve. So there have been a couple of different approaches to try to tackle this. The most common approach is to use a morphological segment of words and then to try to build up a word embedding from that segmentation. So for example, here you see the word unfortunately. The prefix is un, the stem is fortunate, and the suffix is li. One approach by Luang et al. Is to use a recursive neural network to try to build up a word embedding from the corresponding morphological parse. A second approach from Botha and Blunsum from a year and a half ago attempts to learn an embedding for each different morpheme and then to add together those embeddings for the morphemes in a word, together with, by the way, adding an embedding for the word itself. So the number of parameters in those models are actually even more than the number of parameters in a typical neural language model, but they do, in essence, smooth away the issue of very infrequent words by the morphemes playing a bigger role. In our work, we're going to try to take the inspiration from these morphological approaches, but to try to learn a model that works directly on the characters themselves. And this is why I'm trying to draw an analogy to representation learning, because we're going to be learning, in essence, the notion of morphemes as part of this approach. So we take inspiration from convolutional neural networks, and we're going to use convolutional neural networks within the bottom layer of our approach. So here's the overall network architecture. This tells the whole entire story. On the bottom, you see the sentence that we're trying to model, and we're going to be using a recurrent neural network at the very top to model the likelihood of the next word given the words that you've seen so far. Now, in order to represent a single word, we have a convolutional neural network, which I'll describe in the next several slides, which takes the characters of that word and outputs a representation of that word, which is, you could think of as a constructed word embedding for that word. Then we pass that through a highway network to give the input to the LSTM recurrent neural network instead of the word embeddings which would have typically been used. So let's dive down and look at that character level model. So the first thing that we'll do is we'll represent the word as this matrix C for a word of length L, where we have each column corresponding to the character representation, and we use a 15-dimensional representation for every character. And then we have these convolutional filters H. The convolutional neural network will first apply convolution between the matrix representation of the word C and each filter H to produce for every character location, it produces this constant Fi, which we then use a max over time to summarize into a single number for that filter. So here's a pictorial representation of it. That's the matrix for the word. Here's the filter for a filter of width 3. We're going to use filters of many different widths, from 1 up to 7. We summarize that word by taking the convolution of that filter with that matrix as we move one letter at a time down, summarizing it by taking the dot product of that filter with the submatrix for that subsequence. We move all the way down, and this is now a summarization of the filter applied to that whole entire word. We then take the maximum of that whole entire vector to summarize the effect of that filter with a single number, which in this case is 0.7. And we might apply a nonlinearity to that afterward. Intuitively, you might think of each filter as trying to pick out some n-gram from the word. And then the final number is somehow representative of whether that n-gram appears anywhere in the word. So one might then do that for a different filter, and here's an example of a filter with 2 instead of 3. And you're going to then concatenate the output across all of the filters of all of the different widths to get one representation of that word. And that's the analogy of the word embedding that we use. One can then apply the nonlinearity to that before giving it as input to the LSTM. So using this very simple approach, if you were to try to apply it now to this Penn tree bank data set, and if you were to try to fix the number of parameters of the model to be comparable to a word-based model, so here's 20 million parameters, what you find is actually that this very simple character-based model can get perplexity which is as good as the word-based approaches, which we found extremely surprising. Notice it's a bit slower to train, but because you can implement convolutions very fast in GPUs, that helps quite a bit. So the last question we ask is, can one try to learn more complex interactions by the use of this highway network, which was talked about yesterday in the main session? So one could attempt to take the output of that convolutional layer and apply, for example, some nonlinearity. And we did try multilayer perceptrons and got very bad results. Instead, what we succeeded at getting good results from was using a highway network, which in essence has a gating function that tries to decide between carrying forward the output of the convolutional neural network or transforming a corresponding dimension via a nonlinear function. And here's the picture for that highway network of what that transformation would look like. So if you go from using no highway network, we get the perplexity of 84. Using one layer dramatically reduces it to 79, and subsequent layers actually doesn't help very much. So that was all about English, but really the setting is most interesting in morphologically rich languages, and that's where we get our state-of-the-art results. So here we look at languages like Czech through Russian, and we have 2 different data sets, a small and a large one, with varying vocabulary sizes as a function of the amount of training data. So the baselines that we compare it to are this n-gram-based language model, a word-based LSTM, and then we compare it to Boathen Blunson's morpheme model. But because they used a log by linear model, which is a relatively weak language model, we added an additional baseline that hasn't been published previously, what we call the morpheme LSTM model, in order to get a more competitive comparison. So here we see across many languages the perplexity of the n-gram-based language model. Using the morpheme-based approach significantly improves. If you were to use an LSTM, actually does as well as the morpheme-based module. So then we used that improved baseline we came up with, and finally you see here now the character-based LSTM model. And again, we weren't really necessarily trying to get better results. This was really an exploration to see, can one attempt to learn such representations automatically from data? But you do see actually significantly improved results, and with a much simpler method than you would with a morpheme-based model, because we don't have to automatically segment each of the words into the morphemes prior to running our approach. So let's dig down a little bit and try to understand what each piece of the model is doing. So first, let's look at the word representations. So we can try to understand the word representations both before the highway network and after the highway network to see what the effect of that highway network is doing. We try to understand that by looking at nearest neighbor words. So here what I'm showing you are the nearest neighbor words output from the word-based LSTM model. And this is what you would expect if you were to do anything like word2vec or similar. If you look at the output of the character-based convolutional network, what you see is what you would expect in some sense. So the nearest neighbors to trading are words that share characters with it, like heading or training or reading. After the highway network, however, you start to get semantic similarity despite the fact that you might have orthographically disjoint words. So for example, the nearest neighbors to you include things like I and we, which have no characters in common. One could also, using our approach, try to tackle completely unseen words. So for example, here I'm showing the nearest neighbors to look, with many O's inside it, which never ever appeared in the training data. And you see that the model actually can do something very reasonable, which is one of the big strengths of this character-based model, besides the fact that it can get competitive performance with significantly fewer parameters. The last two things we'll look at is to try to understand what is the highway network doing. So one hypothesis we had was that maybe the highway network is simply learning for some dimensions to carry those dimensions and other dimensions to do transformations, but ignoring the actual word when deciding those quantities. So here what I'm showing you is for every dimension of the output embedding, that corresponds to one dot. And I'm showing you what fraction of the time, the x-axis is the average transform probability for that dimension used by the highway network. If it was 1, then it would mean that we're always going to transform the dimension. If it was 0, we'd always carry it forward. But you see that most of the time it's somewhere in the middle. And furthermore, the standard deviation for that dimension is always quite high, which means that the highway network is in essence deciding to either transform or to not transform with very much Bernoulli-based fashion. If you look at the convolutional layer, Max, this is my last slide, and try to understand what is the filter what are the filters that are being learned? Is it actually picking out an n-gram? And so here's a look at such a filter. So what I'm showing you here is a length 6 filter. The 6th character is the end of word character, so I'm not showing you that. And I'm looking at the 100 substrings which hit that filter with the highest strength. And you see that this filter is really focusing on suffixes like ed. However, that story is not always the same. So for example, here's a different filter, and you see that it really tries to look at whether the 2nd letter is T and the 6th letter is an S. And so you get these really interesting structures which are learned automatically by the learning algorithm. Here's a last one. So in conclusion, we think this is a powerful approach to language modeling. There's actually been quite a bit of recent work, notably this paper by Ling et al. That was just published, that also tries to use a character-based language model, except instead of a convolutional approach, they use a bidirectional recurrent neural network to compute the embedding from the characters before feeding to the LSTM. And more broadly, I want you to think about how to use such an approach for other tasks. I think actually that these types of approaches can completely transform data mining as ways to really combine different data elements for predictive purposes or data exploration purposes. Thank you.
Thank you, David. So please, questions? Yes.
I'm not sure if I asked you this at the poster, if it's the same poster, but have you compared your results to bag of letter trigrams approach?
You didn't ask us at the poster because this isn't appearing until AAI. So we have not compared to a bag of trigrams approach, but there's one interesting baseline that we would like to be able to compare it to is one where you would say build a set of n-grams and use instead of using a one-hot encoding for words, use in essence a encoding of the word by what trigrams appear in the word. My guess is that would get a little bit worse results due to the large number of parameters one would need.
Okay, next question.
Did you consider adding a special symbol to the beginning and the ending of the word?
Yes.
Oh, so you used it?
Yes.
Okay, thank you.
Joshua?
Did you notice some... Oh, sorry.
Go ahead. Go ahead.
Did you notice some difficulties in training? Some tricks that you used? Or
Yeah. So
curriculum learning?
So we almost completely followed the training procedure of the Zaremba et al., so Wojciech's paper, which was a stochastic backprop with truncated backprop with a learning rate that decreases once perplexity stops improving. What we found to be extremely difficult to train was the multi-layer perceptron that we wanted to put on top of the convolutional neural network. Everything we've tried failed for training that, but of course, if one were to simply use an identity function, it actually would do pretty well. So we're very confident that it's the optimization which is causing that to not work well.
Did you try batch normalization?
I don't remember, but that would be an obvious thing to try, I agree.
Okay, so last question, if you can keep it short.
Can you say some words about the computational complexity to train your models? Or otherwise, can you scale to hundreds of millions of words or even billions of words?
Yeah, so as the vocabulary size grows, you start to hit the same challenges of any language modeling, neural language modeling approach in terms of having to normalize the distribution. So we made use of a hierarchical softmax for the large model settings, except we used actually a little bit of a simpler hierarchical softmax than has been done in previous work. We simply randomly partitioned the words and then used a hierarchy over that random partition. And we found that that worked as well as anything else. And with that, we were able to scale up quite well.
Okay, so let's thank David again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.